Good morning, children. I am Mrs. Nahi Javeria, taking physical science for class 10th. We are into the second session of Unit 4, Refraction of Light at Curved Surfaces. In our previous session, we had seen what is refraction and how to draw ray diagrams for an object placed in front of a convex lens. Today, we'll be seeing the factors affecting the focal length of a lens. For this, let's perform a small activity. Consider a lens of focal length f. Take a cylindrical vessel of length almost equal to 4 times of the focal length of the lens. Here, the height of the vessel should be greater than the focal length of the lens. Keep a black stone inside the cylindrical vessel. Pour some water into the vessel up to certain height. Here, the height of the water surface from the top of the stone is somewhat greater than focal length of the lens. Now, with the help of a circular lens holder, dip the lens horizontally. The lens is positioned to a small depth from the surface of the water and just above the stone. Move the lens in a way that the distance between the lens and stone reduces. Continue to do this until the image of the stone appears. This proves that the focal length of lens in water has changed and is no more equal to the focal length in air. Thus, it is proved that the focal length of lens depends on the surrounding medium in which it is placed. Now coming to the derivation of the lens formula, you all just observe the figure. Here, consider an object O dash placed in front of a convex lens. O dash P dash is the ray moving parallel to the principal axis. As you all know, any ray parallel to the principal axis after refraction passes through the principal focus. Another ray passing through the optic center goes undeviated. An image is formed where these two rays intersect. That is, I dash is the image. So, O dash is the object, I dash is the image, PO is the object distance, that is U, PI is the image distance, that is V, PF1 is the focal length F, and the triangles P dash F1 and F1 I dash are similar triangles. Observe these two triangles carefully, children. Now, based on the similarity rules, we can write P dash by I dash is equal to PF1 by F1I. But from the figure, we know F1I is equal to PI1 minus PF1. Substituting F1I in the equation 1, we get P dash by I dash is equal to PF1 by PI minus PF1. And also the triangles O dash P and PI dash are similar triangles. From these similar triangles, we can write O dash by I dash is equal to PO by PI. But from figure, we see that O dash is equal to PP dash. Therefore, PP dash by I dash is equal to PO by PI. So from equation 2 and 3, we get PO by PI is equal to PF1 by PI minus PF1. PI by PO is equal to PI minus PF1 by PF1. We are just interchanging the numerators and denominators. Pi by Po is equal to Pi by Pf1 minus 1. So dividing equation 4 by Pi, we get 1 by Po is equal to 1 by Pf1 minus 1 by Pi. Rearranging the equation, we get 1 by Po plus 1 by pi is equal to 1 by pf1. We know PO is object distance, so that is U, and PI is the image distance, that is V. PF1 is focal length, that is small f. So applying sign conventions, we get 1 by minus U plus 1 by V is equal to 1 by F. Again rearranging, we get 1 by F is equal to 1 by V minus 1 by U. So this is the lens formula. Now coming to the lens maker's formula. Observe the figure carefully. Consider a point object O placed on the principal axis of a thin convex lens. Let it be placed in a medium whose refractive index is Na. Let the refractive index of the lens be Nb. Assume that the image is formed at Q if there were no concave surfaces. Object distance is equal to PO, which is equal to minus U. This is according to the sign convention. And the image distance PQ is equal to V, which is equal to X. Let the radius of curvature R be equal to R1. Now N2 by V minus N1 by U is equal to N2 minus N1 by R. NB by X plus NA by U is equal to NB minus NA by R1. Since the image Q of the object due to the convex surface is taken as object for the concave surface, the object suffers first refraction at A and another refraction at B on the concave surface with radius of curvature R2. The ray at B is refracted and reaches I on the principal axis. Now let the object distance U be equal to PQ, which is equal to plus X, image distance PI is equal to V, and radius of curvature R is equal to minus R2, applying sign conventions. Now N1 is equal to NB and N2 is equal to NA. Substituting the above values in equation, N2 by V minus N1 by U is equal to N2 minus N1 by R. We get Na by V minus Nb by X is equal to Na minus Nb by minus R2. Adding equation 1 and 2, we get Na by V plus Na by U is equal to Nb minus Na into 1 by R1 plus 1 by R2. Dividing both sides by Na, we get 1 by V plus 1 by U is equal to Nb by Na minus 1 into 1 by R1 plus 1 by R2. But Nb by Na is equal to Nba. 1 by V plus 1 by U is equal to Nba minus 1 into 1 by R1 plus 1 by R2. Applying sign conventions, we get 1 by V minus 1 by U is equal to Nba minus 1 into 1 by R1 minus 1 by R2, which is the lens maker's formula. Now, based on this lens maker's formula, we'll solve one problem. What is the focal length of a double convex lens kept in air with two spherical surfaces of radii R1 is equal to 30 cm and R2 is equal to 60 cm? Take refractive index of the lens as n is equal to 1.5. It is small n, children. So the answer for this is, we know what is given in the question. R1 is equal to 30 cm, R2 is equal to 60 centimeters, and also n is equal to 1.5. R1 is taken as negative according to the sign conventions, and we know the formula 1 by F is equal to n minus 1 into 1 by R1 minus 1 by R2. So 1 by F is equal to 1.5 minus 1 into 1 by minus 30 minus 1 by 60. Solving this, we get F is equal to minus 40 centimeters. Here minus sign indicates that the lens is divergent, and also it has been stated in the question itself that it is a concave lens. So minus 40 indicates that the lens is divergent. And today's assignment, children, write the lens maker's formula and explain the terms in it. The second question, explain how the focal length of a convex lens increases when it is kept in water. Thank you.